Assalamu alaikum students. Today our topic is related to potential energy of a spring. As shown in the figure, we are having a spring and it is having some mass of m attached to it. So the energy that this very spring is having, it is having only energy once it is either stretched, as it is here stretched from its normal position. This is the normal position. From this very point up to this very normal position. Then it has been stretched through a distance of x, or it has been compressed through a distance of x. From this is normal position, it has been compressed as the turns are very much close, as the turns are very far. So either when the spring is compressed, so if either spring is compressed oblique stretched, compressed or stretched, then there a restoring force gets developed. Or you have to say either when the spring is compressed or stretched, then it is possessing that then spring has elastic potential energy. When this very spring is stretched, just imagine once it is stretched, a force gets developed which tries to pull back the spring to its normal position. Or once the spring is compressed, a restoring force which is called as a restoring force. The restoring force is the force which tries to restoring. Restoring force is the force which tries to bring the body back to its original configuration. So once you are going to stretch it out, the restoring force is going to get developed in this direction. Once you are going to compress it out, the restoring force is developing in this very direction. So on the both sides, this very restoring force, if there has been a small displacement from its normal position, if it is up to this very point its normal position, had it been slightly disturbed through a distance dx, then there would have been a small restoring force. So this very restoring force is try to bring the spring back to its normal position, back to its original position. That restoring force, that depends upon the what? That depends upon the displacement from main position. Then I will say the restoring force Fr restoring is directly proportional to x. If there is more and more displacement, there will be more and more restoring force. If there is small displacement, there will be small restoring force. But there I am going to use a sign of minus. Why minus? The minus says if the displacement is in this very direction, then the restoring force is in this very direction. If the displacement is inwards, then the restoring force is outwards. That is, they are always opposite to each other. Removing this very proportionality, you are going to say Fr equals to minus k times x, where this k is known as spring constant. Spring constant. If you are going to see the dimensions of k equals to f over x. F for that is Newton and x per meter. Newton per meter are the units for what? K, the spring constant. So from this very relation, I will simply say the restoring force directly proportional to the displacement. More the displacement, more will be restoring force. Less the displacement, less will be the restoring force. Now after it, now the external force, which this is the restoring force. The external force that we are going to apply is that very external force is just equal and opposite, because on the application of external force there is a stretching in this very spring, or there is compression in the spring. Then because of that very external force there is a restoring force developed. So we can say F external equals to what? Minus times F. Or if we are going to use what? The vector form, because they are equal in magnitude but opposite in direction. So this F, or what I mean to say F restoring, if we are going to use it, well, why there is minus? The minus is because F external and F are, they are always opposite to each other. So F external equals to minus times of minus of kx, then it will be simply what? Plus kx. Now this is the external force that equals the spring constant times the displacement. Now let us assume that this very spring is slightly disturbed through a distance of dx. Once it is slightly disturbed through a distance of dx, then there will be a small amount of work done. That dw will be then equal to how much? That will be simply dw equals to f external dot of dx, or you will see that it will be simply f external into dx cos of 0. Cos 0 is 1, then dw comes out to be f external, that's kx x, and we are having what into dx cos 0, that's 1. So this will be the dw, but this is the small amount of work done when this very spring is displaced through a small distance dx. But as we know, the spring is displaced from x is equal to 0 to x is equal to x. So we have to integrate this very equation in order to find out whole. We'll say dw, integral of dw equals to integral of 0 to x kx dx, which implies w equals to differential integral w equals to k is constant, and the integration comes out to be there only to the x. It's x2 by 2, 0 to x. So w comes out to be what? It will be k, instead of x we are having x, it will be x square by 2 minus times 0 square by 2. So simply w comes out to be 1 by 2 kx square. So this is the amount of work done which gets stored in the form of spring once it is stretched. So this is the equation for elastic potential energy. Now you have to remember, elastic potential energy is never negative, and elastic potential energy increases when the spring is stretched or compressed. Elastic potential energy increases if what? If spring is stretched oblique compressed, or you are having the potential energy, lost potential energy of a spring. Once the spring is in the relaxed form, that there is neither compression nor there is extension it nor there is stretching it, then the elastic potential energy is 0. This is all for today. Tomorrow will be with another lecture. Till then, Allah Hafiz.